So I wanted to start by talking about functional groups.
Wait, are you recording?
Yes.
Oh, we've been having this whole conversation.
No.
Oh.
I just talked about functional groups with my OChem 1 last night, and I kind of want you guys to define it. How do you define functional groups?
How do we define functional groups? What you said?
Yep.
Things that make science.
Things that make science?
No, I'm just reading your thing. Hold on.
I think you have a grasp on what it is, but what is it? Yes, Belen?
A specific set of atoms with specific bonding characteristics.
Nice. Good. Specific set of atoms with a specific bonding pattern that give unique characteristics like reactivity. So one of the questions that might have come up on your unit test had a compound like this with options of what functional groups could be present. And if it listed alkene as one of the possibilities, would you select it and say, yes, this compound does have an alkene? The atoms that are needed, the bonding pattern that they need to be an alkene is carbon-carbon double bonding. There's carbon-carbon double bonding. So why is it not an alkene? It has different characteristics. The pi bonds of an aromatic ring are not reactive in the ways that the pi bonds of alkenes are reactive. So despite having a similar set of atoms with bonding characteristics, bonding patterns, it has different characteristics, so it's a different functional group. So no alkene in this compound. Instead, the hydrocarbon functional group is the aromatic ring.
I know, so I was like
Sometimes aromatic rings are grouped into a different name for their family. These are arenes. And that term arene is where we get the term aryl. And aryl is what we'll use to describe things that are connected to aromatic rings. So for example, we might call 2-chloropropane an alkyl halide. And we'll call chloroethylene a vinyl halide. But we'll call bromobenzene an aryl halide. Yes, Ozzy?
with acyl, isn't it because it's adjacent, right? Isn't that how you defined that previously?
No, actually, that's a good question. There is kind of an overlap here of being an alkyl halide relative to an alkene. This is an allylic halide.
Okay, that's what I was wondering.
Right. So it's technically an alkyl halide, but because of its position relative to an alkene, the fact that the halide is adjacent to the alkene carbons, it's an allylic halide.
Is that where you get benzylic with one off ring?
So benzylic, we could say, is the combination of alkyl and aryl, if it's on an sp3 hybridized carbon, and that carbon is adjacent to the ring, then we have a benzylic halide. Okay, on your worksheet, we're going to start with the side that has reactions. And we're going to start by going through the reactions for chapter or section 15. In fact, we'll typically refer to this as benzylic reactions. And so this was exactly like a perfect segue for us. The benzylic reactions are influenced by the presence of the benzene ring. So these are things that happen adjacent to benzene rings because of the benzene ring. I want to start with some review reactions that we have technically already seen. We can do acid catalyzed hydration. And I want to point out the regiochemistry that is relevant with the benzene. So we start with this aromatic ring that has an alkene attached to it. The two carbons of the alkene differ in substitution. The benzylic position is less substituted than the non-benzylic position. When we run acid-catalyzed hydration, we have to consider the carbocation intermediate that forms. There are two possibilities of what carbocation intermediate can form. A carbocation can form on the left-hand carbon. That creates a tertiary carbocation, fairly stable. What type of carbocation forms for the carbon on the right?
Secondary.
Good? Great. Secondary benzylic. Being a benzylic carbocation will mean resonance with the aromatic ring, which makes it far more stable than just a tertiary carbocation. So this is what I want to label about this. This makes a tertiary carbocation good but not great. And this makes a secondary benzylic carbocation. More stable, more likely to form. So you'll remember Markovnikov's rule says hydrogen adds to the carbon with more hydrogen. And this is a Markovnikov addition reaction. But we're going to break Markovnikov's rule, and we're going to show the hydrogen adding to the carbon with less hydrogen. Markovnikov didn't know what he was talking about anyways. So it's fine that we're breaking his rule.
And we break that just based on the reagents that we use?
Yeah. Acid protonates the alkene, gives us a carbocation intermediate, and that's going to be at the more stable position. Okay, similar to this is the HX addition reactions. If we start with that same alkene, again, we see that the regiochemistry is not what we'd expect, being Markovnikov versus anti-Markovnikov, and that's because of that benzylic stabilization of the carbocation. And as I say that, I think about how I want to show how that carbocation is stabilized. Not going to draw all of them, I'm just going to draw one of those resonance forms. When the carbocation forms at that benzylic position, just off of the ring, the aromatic ring can take electrons and send it out to that positive charge. Delocalizes the positive charge, gives us resonance forms where the carbons inside of the ring are holding on to the charge. Makes it more stable, means the carbocation forms more readily. Okay, let's talk about substitution. The second reaction that I give you has two different types of halogen groups. How can you describe the halogen that is connected directly to the ring? Sorry? Aryl halide. And the other one across from it? Benzylic halide. Let's treat this with methanol. We have two different halogens, but we find that they don't both substitute. The benzylic halogen goes through substitution, and the aryl halide does not. That's to point out the difference in reactivity for regiochemistry. Benzylic halides go through SN2, SN1 readily. Aryl halides unreactive to SN1, SN2. Our third reaction, radical halogenation. How many benzylic positions in this molecule? No, not quite. 2. 2 positions right off of the benzene ring, benzylic. 2 positions that are further off from the benzene ring, non-benzylic, really just alkyl. When we treat this benzene with Br2 and light, we get radical benzenes that take off a hydrogen and then substitute bromine at that position. There are 2 different benzylic positions. The more substituted benzylic position is the more stable radical intermediate. So we halogenate the more substituted position. There is a different reagent that can be used at these benzylic positions. NBS is short for N-bromosuccinimide. And N-bromosuccinimide can be used as a source of radical bromine if you don't want to work with Br2. Any idea why you wouldn't want to work with Br2? Carcinogenic. Yeah, it's also a very strong oxidizer. We have some Br2 upstairs. We used to keep it in one of the metal cabinets under the fume hoods in the OChem lab, and that cabinet is just covered in rust. You open the drawers, everything inside of it is just covered in rust. So Br2 is kind of hard to work with. NBS lets you get around that. Similar to last time, I want to point out why the intermediate that forms here does, and the intermediate that we get in this reaction is that most substituted carbon radical. When you show arrow pushing for radical reactions, we have to show one electron moving at a time, so we use fish hook arrows. And instead of having two tips, it just has one. Two tips shows two electrons, one tip shows one electron. And this time the ring takes part in that radical moving around one electron at a time.
Is that a 2?
A 2 where?
In the half arrow.
No, it's a half arrow.
Oh, I see.
I can see how it looks like a 2. The 2 electrons of that pi bond are going in different directions.
Okay, I see.
Hmm? You want one more methyl. You don't need it. Thank you. Sarah?
So for the BR2, it's also the same thing, right? That radical forms
Yep,
that spot,
exactly.
and then the okay.
The only thing different between Br2 and NBS is where the bromine radical comes from. NBS will kick off the bromine radical, and then the nitrogen will take the hydrogen. But I'm not going to ask you to show them the mechanism for this reaction, but sometimes seeing the intermediate is useful. Malena. Oh, great question. No. So what you're getting at here is something that we did cover last week when we were looking at reactions. We showed that halogenation of allylic positions, radical halogenation of alkenes, gives 2 different alkene structures because there are 2 different radicals in resonance with each other that can react and form. This reaction has a radical on the most substituted carbon, and then it has a radical on 3 carbons inside of the ring. So you could, in theory, expect that this radical that I've shown second does react, and you get a product like this. What functional group is present in this reaction, in this product? An alkene, and not an aromatic ring. So the fact that aromatic rings are different from alkenes hints to us that there is something special about aromatic rings. The fact that an aromatic ring can partake in resonance doesn't mean that those resonance forms are more reactive forms or even equally reactive, but there's actually something so stable about reforming the aromatic ring that these intermediates never form. So this is just an aside from our reactions. But if we were to plot the energy to form this product versus this product, the one that we expect. Here's the energy to make this product. Actually, I'm sorry, the intermediate is going to be all at the same spot. Okay, this is the hard part. Forms a radical intermediate. To form this product, actually it doesn't even come down this low. We have to go up in energy to here. But when we form that same intermediate, and when we reform the aromatic ring, we go back down in energy. So the aromatic ring accounts for this stabilizing force. Destroy the ring, you have to go up higher in energy. Reform the ring, and you stay down lower in energy. And this is a stabilizing force that aromaticity is associated with. When we say things are aromatic, we mean that they have this intrinsic stability. I want to come back later to that more. Okay. Those are reactions that we've seen in the past. And now we're just seeing them applied at the benzene position, the benzylic position. There are two reactions that we have not seen before. The first one is benzylic oxidation. Benzylic oxidation requires one specific thing. This requires that the compound has a benzylic CH bond. If there is no CH bond, benzylic, then these oxidation methods don't work. You'll notice that this next compound has two different carbon groups. How many of those carbon groups has benzylic hydrogens? Just one of the two. To oxidize that carbon, which means pulling out hydrogens and putting in oxygens, we can either run potassium permanganate, and this has to be run hot, and it often runs for 24 hours, or we can use chromic acid, and chromic acid works a little bit faster. I do want to point out that that is not actually chromic acid. But it is the reagents that you can mix together to make chromic acid, because most people don't really want to sit on chromic acid in their lab. They'd rather make it as needed. Okay, so there's two positions, one that has benzylic hydrogens, one that does not. After this compound sits in reaction with chromic acid for a few hours, we find that one of the positions has been oxidized completely into a carboxylic acid, and the other position had no change. It started as a tert butyl group, it ended as a tert butyl group. There's something cool about this process, which is that it doesn't matter how many carbons are on that benzylic chain. So if you want to change this up a little bit, here's something that you can do to modify what we understand about this reaction. If there are other carbon groups coming off of this, you get the same product. Those carbon groups get cleaved off during the oxidation process. It doesn't matter how many carbon groups are coming off or how large those carbon groups are. Every benzylic carbon becomes a benzoic acid position, unless there's no benzylic hydrogen. In that case, there's no cleavage, there's no oxidation. Cool, right? So one question that might come up then is, what happens to all those other carbons? Where do they all go? I mean, they basically just create a waste byproduct. They get cleaved in half. I want to show you one last application of this that's actually not on your sheet. Let's take this bicyclic structure, and on one half we'll have an aromatic ring, and the other ring just has alkyl carbons, sp3 hybridized. Let's oxidize it with chromic acid. Tell me.
Can I ask this quick question?
I bet it's not stupid. Let me hear it.
What do you mean by benzylic hydrogen?
Good, no, that's a good question. Ozzy?
I actually have another question.
Oh, okay. Let's answer this one first then.
Does it mean the next carbon that has a hydrogen attached to it? That's a good way of
Right.
What is that?
There's a lot of CHs in the world. There's a lot. This CH is sp3CH. This CH is also sp3CH, but it's adjacent to an aromatic ring. So we refer to that type of position as benzylic.
Okay, so just a carbon with a hydrogen in the benzylic position.
Correct. Okay, so do you see how this benzylic carbon does not have a CH? Because of that, it is inert to the oxidation. The oxidizer pulls off a hydrogen to begin this process. If there's no hydrogen, there's no oxidation.
So my question was, because there's two
Yep.
on this, so does it choose still one or the other?
Nope.
Or is it gonna do both at the same time and cleave off the rest?
Good. Every benzylic carbon gets oxidized into a benzoic acid. And since I have two benzylic positions here, I get a dicarboxylic acid product.
Hey, that's kind of like how ozone kind of does that, like, you know how it breaks that?
Yes, very similar. So there are two other carbons that were in the starting material that aren't anymore. They've essentially just been charred. They turn into a tarry byproduct. Okay, so we can oxidize benzylic positions. The other new reaction for us is reducing benzylic positions. This is going to be limited to aldehydes and ketones. And I'm going to abbreviate aldehyde and ketones using chemistry abbreviations. Lily?
Just to confirm, it doesn't matter how many benzylic hydrogens there are attached to the benzylic carbon. Those
Good.
It's the same as the carbon.
Correct. So
Cleaved away.
originally I gave you CH3, so there were 3 benzylic hydrogens. Then I changed it so that there's 1 benzylic hydrogen. Here is an example with 2 benzylic hydrogens. The oxidation process, the carbon-carbon cleavage process, gets kick-started by the oxidizer if there's a hydrogen that it can pull out. But if there's no hydrogen, then it can't do anything. Katie?
Is it limited to only like 2 spots on the ring, or like
No.
so it could like potentially go on all
Totally.
Okay.
Yep. If you create a polycyclic structure where there's a carbon group at every point on the ring, yes, you could oxidize all of it.
Interesting.
Hexabenzoic acid.
Sounds hectic.
Sounds a little scary. Yeah.
If it had more carbons or hydrogens, would it like affect how fast it happens? Like,
Well, so yeah, if you're oxidizing, like in this bottom example, if you're oxidizing twice as many places, you can expect the reaction will need to go on longer because you have more work to be done. So a practical setting, well, I think it will depend on a lot of things. Other places, other people on the internet will refer to this reagent as Jones reagent. Chromic acid will be called Jones reagent. I don't really ever call it that, so if you see it somewhere else, just a heads up. Benlin?
So you said it can be a CH bond, right? It can be like a CH, like a CH2 or a CH3.
It can, yeah. We started with CH3, but it's the CH, there just has to be one. It's that bond that kickstarts the oxidation process.
I can tell we're all very excited about our new segment.
And why do you think that the benzylic position is important for that process? The intermediate that forms, just like the last two things we saw, the intermediates that form are more stable intermediates because the intermediate is utilizing that benzylic position. It's utilizing resonance with the aromatic ring. All right, reduction. I do want to point out that this is not reduction of benzylic aldehydes and ketones. It is the reduction of aldehydes and ketones. We're going to look at it in the next two chapters within this context at benzylic positions. But we're going to come back to it later in the semester and utilize it in all sorts of contexts. So I want to point out that this reaction, unlike benzylic oxidation, which places a radical on that benzylic position and benefits from the stability of the resonance of that radical, this does not change because of the aromatic ring. It is not the aromatic ring that allows for this reduction to happen. Yeah.
Can I ask a different question about the previous reaction?
After I get the chemicals on the board.
Okay.
So we have two different ways of doing this. One of these methods is called the Wolff-Kishner reduction. And the other is called the Clemenson reduction. But they both give the same product. In this case, the aldehyde is reduced to a methyl group, and the ketone is reduced to just an alkyl chain. The Wolff-Kishner reaction, I also like to call hydrazine reduction, because that's the chemical that we'll actually use. Do you guys know hydrazine at all? Rocket fuel. Yeah, it's nasty stuff. It's hard to work with. But it's a great reducing agent.
So one is a subcategory of this, right? Like we're not moving on to anything.
No, I'm just saying the reagents, maybe I should have shown this a little bit different. The reagents for the Wolff-Kishner reduction. But I think a better name for Wolff-Kishner reduction is hydrazine reduction. The reagents for Clemenson reduction a mixture of hydrochloric acid with zinc and mercury So I really do think that we could name every reaction by just the reality of what's being mixed together. This one just doesn't sound cool, like metal in acid reduction.
I think wolf sounds cool.
Sure, Wolff-Kishner.
See that?
Oh,
5 times fat.
I spelt this guy's name wrong. Sorry. Kishner. I forgot the N.
And I spelled it correctly.
But that's the thing, it's like it's someone's name that doesn't tell you what's going on. Hydrazine reduction tells you, I need hydrazine. And at least you learn a little bit about rocket fuel. Okay, so 2 different reactions, they do the same exact thing. It's just a process of what your reducing agent is. All right. What I want you guys to spend some time on is this reaction roadmap. So I've given you all of the intermediates, and I want you to fill in the reagents. This will use reactions from this, but also reactions that we reviewed back in the OChem 1 review. I want us to be on this until 10 after, so for the next 15 minutes or so. In that time, feel free to take your break. I'll give a 5-minute warning too. Take your break, use the bathroom, get your blood flowing, but see how many of these you can solve the missing reagents for. You're welcome. I just realized I forgot to upload this worksheet, so I'm doing that now. Do you mean NaNH2?
Yeah, I do mean NH2. Just, I remember NH something is a strong base.
Mm-hmm.
So, just trying to remember what it was.
3 hydrogens will leave the nitrogen neutral,
Right.
but 2 will give it a negative charge.
Yeah, that's right.
Great work. Good.
And then I said chromic acid in this one and then Wolff-Kishner because that's the only one on here.
Good. Perfect.
I was trying to figure out what do you mix with that so you have a less substituted cation?
You know what? I just noticed a mistake I made here. That's impossible.
Yeah, I was also trying to.
So actually, this is the one you'll need to look back at, the OChem 1 notes, the reaction notes from OChem 1 from last week, because all that you know is you can't use the one that I gave you today, because it absolutely would have put the alcohol here.
Yeah, and I'm trying to think back from OChem 1. I just don't remember. I mean, you can just look at it.
Yeah, if you've got notes, that's a good way to review. Hi.
Going over like the Benzylic nomenclature.
Yes, we are in the second half.
Oh, okay.
Why?
That's the part that I reviewed before I came in here.
Like orthopara, orthometapara.
No, like the names for the benzene.
Like naphthalene and phenanthrene and,
You were talking
or these.
Yeah, like this was like bromobenzene, chlorobenzene.
Yeah.
This was okay. And then you were talking like why is benzene not a alkene?
Yeah, we did talk about that.
Oh really?
Yep.
Okay, I see.
I was gonna ask you about this. How would the arrows work with this? Would it be the H coming here and the BR going there to get this part?
Mm.
The H goes away.
So it actually will be more than one step.
Okay. The 2 steps.
So first the oxygen needs to bond to carbon. So we'll show the lone pair on oxygen in that nucleophilic attack.
So it goes here.
Perfect. And that arrow's perfect. But that means we get an intermediate. Oxygen has made its new bond to carbon, but oxygen still has 2 other bonds. A 3-bonded oxygen has a positive charge. Then that oxygen gets deprotonated in the last step.
Would it go no more substitute?
Well, there's only one
This
carbon.
goes away, so then this would be like, would it look like that? When the BR goes away and the
Well,
oxygen comes in?
let's show the bond to oxygen now. Oh, but I think your carbon disappeared.
Well, yeah, this one disappeared.
Well, this carbon off the ring,
Okay.
and then bromine. But here, there's no carbon off the ring.
I'm confused.
How many carbons?
There's one. Well, there's one. And the bromine's coming off this carbon.
And then with what you just had, let's go back. How many carbons?
None.
0.
Okay.
So draw in that one carbon that was there, and now bond it to the oxygen.
So it'd be
Yes. And then also draw two other bonds.
like
Mm-hmm.
just coming
Good.
off of it because of this.
One of them is H, one of them is CH3. Good. And that's why it has a positive charge.
So the final product would have a positive or no?
Nope. Now bromide comes in and acts as a base and deprotonates the oxygen.
It would come here.
But to take the proton. So its arrow goes to hydrogen. Good.
So that goes away. Okay, okay.
Forms a bond and then breaks this bond. Hydrogen now needs to break its bond to O.
So this would be. You said this bond needs to break? So
Mhm.
then you would go like that?
So this means that hydrogen takes the electrons away from oxygen,
Okay.
but oxygen is more electronegative. So
Yeah.
oxygen should take the electrons away from hydrogen.
So then you
So we'll show that arrow going to O instead.
like that.
Perfect.
Okay. And then so this would just be the CH3.
Yep,
And
that's
then
your final product.
And then this would be the BR on the side. Do you have to show the
HBR.
Like, do you have to show the H, like the byproduct?
Yes.
Okay.
Perfect. Good work.
You didn't go through like the arrow stuff, so on your exams or whatever, are you gonna want them? Or?
There are going to be specific problems, specific mechanisms that you'll be asked to show, and it's not these.
Oh, okay.
Are these all anti-Markovnikov addition?
Nope.
Okay. I
This
thought-
one is. Yep.
Yeah. So they're all different too.
Yeah.
Okay.
Some of them have nothing to do with Markovnikov. Actually, only this one does.
Oh, okay. And this is just benzylic. Okay.
Yeah, that's what today we're looking at the reactions that benzylic positions are useful for or useful with.
stuck on the second one. We're thinking it's this.
What does the OK mean?
Strong base, weak nucleophile.
Oxygen and potassium. This potassium. This is potassium tert butoxide.
So you were right. Andy, okay, that's okay.
Oh.
You were right.
On what one?
The terp butoxide. I can't talk today. It's been a long day.
Right there?
Oh, you guys already cut? Yeah, okay.
This
Yep.
is the only one we're stuck on.
Oh, right.
I did make a mistake, sorry. It was during the oxidation. Yeah.
So it shouldn't have that methyl.
It should not have that extra methyl group, which means that the next step also should be short by another carbon. Sorry. Stand up for yourself.
Concussed. Yeah. Yeah. Plastic stuff. Car accidents, soccer, snowboarding, unfortunate car hood accident.
Are you allowed, do your parents let you play sports still?
Bummer.
Like my parents won't let me stay on a soccer team.
I mean, if I don't know.
Anybody want to put answers on the board? One apiece? First come, first serve.
Should I do the hardest one or should I leave that for someone else?
Come on, Max, take
I
it.
don't know if it's right though.
Show yourself.
If it's right, I want you to correct me though.
You know, there's some classes that like, some of you guys might know. Some classes that like list the class. Like list your academic standing in the class. Well, they don't say names, but they like give different. Nice, Max.
There you go. Oh, you already have-
You're right. You did take the hardest one.
Wait, is it right? I don't know if it's
Yeah, you nailed it.
Alright.
Perfect. Good. Great. Wow. Yeah, there's 6 more. Come on.
Did you figure it out?
Oh, other side.
Is it?
That's a good excuse.
Yeah, that looks right. Yes, I agree with you on that.
Sorry. Blue is kind of purple. It's nowhere near purple. No, just one.
Is PDC palladium? Or like the PD/C?
PD is palladium.
What's the /C?
C is carbon. Lily, you gonna take it? No. No? Come on. Really?
The ketone one right there?
Oh, we are. We got two more.
That one's ketone.
Ketone. Oh, sorry. I guess I don't. You want me to write ketone?
Oh yeah, no, never mind, hold on. No, it is where it's at. Okay, no, the wolf. I was talking about the wolf. So I'm not confident. Don't ignore me, I'm afraid.
That's okay. You don't have to be.
Oh, yeah. Or you can say K.
Great. Perfect. For this last one, yes. Ozonolysis. Or you can use zinc instead of DMS. Okay, I do want to point out one thing. I can totally understand why why you would write Wolff-Kishner. That is how I presented it. And actually, maybe this was a bad way of representing it, because you guys know that there are a number of reactions like hydroboration oxidation where you have to say first, then. You have to say first, second. And I want to point out that this is not a first, then scenario. We're not saying first run Wolff-Kishner, then run Clemenson. I actually just meant to say that there are two ways of doing that. And normally I say that with this or, but I didn't do it for this. So I do want to, and I don't want to feel like I'm coming after you for this. I want the reagents. So instead of writing Wolff-Kishner, RIP Wolff and Kish. What do you mean?
I was just saying that because you can use like two different sets of reagents, like the K and the or hot or that. It's just saying that you could use the
Right.
one or the Clemenson one.
Do you want to take this starting material to this product? You can use potassium permanganate or chromic acid.
Oh, so you get the same exact.
Correct. Same thing here. You want to take this and reduce both of those carbonyls. You can use hydrazine in base or hydrochloric acid with metal.
Is the Clemenson one the hydrochloric acid one?
That's right. So the first is Wolff. Sorry. Okay. Questions on that reaction roadmap? Instead of Br2 in light, what else could I have used? NBS in light. Instead of tert butoxide, what else could I have used? Strong base and heat, like sodium hydroxide, would work great there too. Tert butoxide is perfect. Instead of hydroboration oxidation, what could I have used?
Can you use H to?
No.
Okay.
Oxymercuration reduction?
Yeah, well, because I was thinking that you added the OH and I was like, okay, never mind.
Sorry, trick question. There's nothing else you could use. Unless you did anti-Markovnikov HX addition and then substituted. So if you want to do anti-Markovnikov hydration here, that's really the only way. How else could I have done dehydration? There's no other way, just the sulfuric acid. Got you guys twice. Okay, hydrogenation of the alkene. Any other method? No, that's it. Chromic acid. to oxidize that 2-carbon chain into a benzoic acid? Any other way we could do it? KMNO4 for like a day, or the chromic acid probably in an afternoon. Okay, this was the mistake I made. I accidentally had an extra carbon there. Was there any other way besides ozonolysis that we could get to this aldehyde? Could I have done chromic acid? After all, there is a benzylic CH. That, if anything, would give me a carboxylic acid, and it wouldn't leave me at the more reduced aldehyde. Okay, and then hydrazine could have also been hydrochloric acid with zinc and mercury. Okay. Did you guys all get your break? I think I realized I forgot to say go take it. Do you need a break? Go take it. Otherwise, I'm going to jump us into nomenclature. Yeah.
Oh, can I ask you a question?
Yes.
About with like the benzylic like hydrogens that it takes. So for
Yeah.
like the bottom one, because there's 2 benzylic hydrogens on both carbons.
Yeah.
It takes both of them.
That benzylic CH is just what's needed to kickstart the process.
Okay.
The oxidizer comes in and takes off that hydrogen, and it leaves a radical.
But like, would it take off both hydrogens?
Just starts with one. And then the rest of the process doesn't matter what else is attached. The rest of the process just does more bond cleavage. But forming that first radical requires having a CH.
Okay. Oh. So it doesn't matter if there's 1, 2, 3. Like it just needs one.
Yep. You're welcome. Yes.
Can you explain the O3 part again? What you said that part, but then you said we could do something else with that. And I didn't quite.
Oh, I was saying if you tried chromic acid, because it does look similar to the oxidation, if you tried to go with chromic acid, you'd end up with a carboxylic acid and not an aldehyde. I just wanted to point out, it wouldn't be crazy if you looked at this and thought, could I use that new reaction of benzylic oxidation? And the answer is no.
Yeah, because it makes the aldehyde. Okay. So
Yep.
I was really confused. I was like, wait a minute, I'm actually not trying to. Okay, and then you said on that we could use any strong base, right?
Yep.
From that.
Like sodium hydroxide would work there as well.
Okay, that's what I.
Alkoxides.
Was this terbutalsite only used for like anti-Markov? Because it was so bulky that it like resists.
It's good for anti-Markov or anti-Zaitsev elimination. But here, people would argue that tert-butoxide is better than any of the other strong bases, because here it won't do substitution, and there's only one elimination product. There isn't the choice between Zaitsev and anti-Zaitsev. There's just the one product. So this won't substitute. It'll only do elimination, and there's only one elimination it can do, so it's actually a great option here.
Because it's so bulky.
Yeah. Yeah, it'll only serve as a base. Thanks. I knew I put the nitrogens all together, but I didn't know if they came next. All right, are we ready? Yes. Oh, Elliot's not here. Do you guys know why I used pH in my abbreviations there? Right. So this terminology, we have benzene is our smallest, simplest aromatic ring. Benzylic represents something attached off of the benzene ring. And phenyl describes the aromatic ring as the substituent. Great. Personally, I would have done it differently. I think benzylic sounds like what phenyl should have been called, but it's okay. So we can abbreviate benzene rings whenever we want to by showing pH if it's just the benzene ring. But as soon as things start to become more substituted, I can't abbreviate a benzene ring that has another group off of it with pH because it stops being phenyl and it starts being a substituted phenyl. So to show the regiochemistry, to show the locant set, the positions of the groups, we don't do it for anything that has another substituent. What I want to give you guys are some of the common names in addition to the systematic names. What I like to say though about common naming is that I won't grade you on needing to show or use the common names, but I may ask questions where knowing the common name helps you know the answer. So I'll never make you write the common name, but I may need you to understand and interpret the common name. However, systematic naming I will always accept and think is important. So benzene, with just a CH3 coming off of it, this is methylbenzene. Do you think that is a common name or systematic? Really? That seems pretty systematic to me. Well, that's right. So if our parent chain was the CH3, then we would call it phenylmethane. But here, methyl is a substituent, benzene is the parent chain, methylbenzene. Common name is toluene. How'd you get that? No idea. Right. Mm-hmm.
On that methylbenzene, off the methyl group on the other side was an alcohol. That would then make the methyl the parent chain because the higher priority group is the alcohol.
Yeah.
Okay.
Yeah, if it was CH2OH, it would be called phenylmethanol.
Okay.
Mm-hmm. All right. The next one is referred to as vinyl benzene. Vinyl there is telling us about the 2-carbon chain of the alkene, but its common name is styrene. And it is the precursor, the monomer to polystyrene, styrofoam. With our halogens attached, we just call them halobenzenes. So this is chlorobenzene and bromobenzene. There really aren't any common names for them. Nitrobenzene also doesn't have a common name. Just call it nitrobenzene. But the NH2, the amine group, Systematic name is aminobenzene. Do any of you know its common name? If you're in the lab, you might recognize it. It does not start with an N. No. And in the first week, yep. Well, and it was a version of this compound. It had it in there. Its name is aniline. You guys worked with dimethylaniline with NCH32 instead of NH2. I always get aniline mixed up with alanine, the amino acid. Which, I mean, it doesn't happen a lot, luckily, but. Our next one is cyanobenzene. There's not a common name that I'm going to use for it, so I'm not sure if there is one that we use often. We have hydroxybenzene. This one has one of the worst common names of all time. Its common name is phenol with an OL, not to be confused with phenyl, which is to describe benzene as a substituent. Anytime you have an ether, you can refer to that substituent systematically as alkoxy. So this is methoxybenzene. But its common name is anisole. How many others? Oh, right. Okay, with a sulfonyl group attached, we just call this sulfonyl benzene. An aldehyde attached. And you know what? This is like, this maybe will feel a little bit more like a common name than systematic. But it's the only version of naming benzaldehyde that I'll have you guys do. Benzaldehyde, a benzene with an aldehyde coming off of it. And then similarly, when it's a carboxylic acid, benzoic acid. Okay, so these are all of our monosubstituted benzenes. When we have di-substituted benzenes, we have special nomenclature to represent the position of the two groups. We use ortho, or we can abbreviate it as O, to describe a 1-2 position on the ring. Meta, or M, describes a 1-3 position. And para, P, describes a 1-4 position. So we use these terms only if there are two groups, no more, no less. If there's more than two, then we start using typical IUPAC nomenclature, and we give the lowest locant set. And I want to talk about the locant set for common names. If you want to use a common name while you're naming a highly substituted benzene group, whatever group is responsible for that common name, for instance, you want to use toluene, the methyl group is responsible for toluene. You want to use aniline, the amine group is responsible for aniline. That is where your locant set starts, and you go for the lowest locant set surrounding that position. It gets a little awkward and strange sometimes. So practice is good. Here's what I want you guys to do. I want you to come up with 2 di-substituted compounds and 1 with 3 substituents or more. And I want you to name it using ortho, meta, and para nomenclature. And then with another group, I want you to, well, actually, no. I think I'll come and take some of your examples and we'll work through them on the board, taking the name and drawing the compounds. So in your groups, 2 di-substituted and 1 that is tri-substituted or more. Using these substituents, come up with 3 compounds.
We just did one last lab, didn't we?
Can you do it in 6 minutes? No, it's okay. It happened yesterday too.
Well, everyone's just gonna watch it. It goes for a ride. All of a sudden, they're gonna be like, "Wow!" It's good that it was on break.
Mm-hmm. When naming it, pick 2 groups, put them on the molecule, put them around a benzene, and name it. And then pick 2 new groups, put them around the benzene, and name it. And then pick 3 more groups, put them around the benzene, and name it. It's hard not to. Good. Good. Great start.
Is that how you do that?
Mm-hmm. Perfect. Super easy. Yeah.
Why do they invent these things instead of just using positions? Like, it seems like it's more confusing to come up with this shit than just use
The numbers?
1, 4.
I don't know. What I do like about ortho, meta, para is that you don't have to worry about what locant you give to what substituent. So you don't have to prioritize. You don't have to say 1 bromo, 4 chloro benzene. You can just say para. I think it probably came down to when they were learning about structural determination and realizing that different compounds could be the same chemical formula with groups just arranged in different places. They might have been working with a series of isomers that already had names, and then they just used that to explain kind of like back naming. I don't know. Yeah.
Like, we could use that one we did from left bird.
Yeah. Oh, yeah, yeah. I mean, we didn't talk about how to name the ester. But if you change the ester to a carboxylic acid.
But that's still the dye, right?
Mm-hmm.
I use how, like the OMP. Okay. Do you want that? I don't do the 1-3.
Yeah, yeah. Right. Perfect.
When I saw that, I was like, oh, I know what that is.
Good.
With the sulf. Sulf.
SO3H. Okay. I don't know if I'm just making stuff up, to be honest.
Mm. So actually, we'll put the nitro in front of benzoic acid.
Why?
So benzoic acid is the name of the compound, and it has a nitro substituent. I want to talk about giving some of these compounds names using the new orthometapara versus using the old locant positions. For this first compound, nitro is just going to be a substituent in the prefix, whether it's on benzene alone or whether it's on benzoic acid as a root name. Benzoic acid can't be listed as a prefix. It's very challenging to say that there's a carboxylic acid on my benzene without saying benzoic acid. So when we name this compound, we use nitro as a substituent to describe benzoic acid. Because benzoic acid is kind of that common name that I'm using, my locant set starts at benzoic acid and my nitro group is at position 3. So we could call this 3-nitrobenzoic acid. And I don't have to say that the benzoic acid is at position 1. Of course it is. It is responsible for the root of the compound, so that is position 1. So the nitro is position 3 relative to benzoic acid. But because it's a 1-3 relationship, I can also call this M, or meta nitrobenzoic acid. Also, I want to take a second to show you what nitro looks like, because we will be dealing with it a bit. Nitro is a positively charged nitrogen in resonance with 2 oxygens with a negative charge. Ozzy?
I was going to say, because the oxygen, that's why we start at 1, right? Because the electronegative.
No, it doesn't have to be because of what's more electronegative. We start here. This is position 1 because we're going to call the parent chain benzoic acid.
Oh, parent. Okay, sorry, I missed that. I apologize.
Okay, the next one. The groups are positioned 1-4. I can go in and refer to these as amino and methyl. So I can call this 1-amino 4-methyl benzene. Very systematic. No question about where anything is. But I could also just refer to this as para aminomethylbenzene, or I can refer to the parent chain by one of their common names. So I can call this para-aminotoluene. Or I can call it p-methylaniline. Love it. So many right answers, all for the same thing. So when I say that I'm not going to require you to name using common names, I mean that the correct answer won't be para-aminotoluene, but you may need to read a question that says, when working with para-aminotoluene, and know what toluene is telling you. Okay, my last one. I can't use ortho, meta, or para descriptors here because I have more than just one substituent. Obviously, my lowest locant set is going to be 1, 2, 3. And I can go from either direction, so I will go whichever way gives the first alphabetically the lowest locant set. So 1 bromo, 3 cyano, 2 sulfonyl benzene. Keep practicing with those groups because they are going to come up more in our next section next week as well. All right. The last thing I wanted to get into was a discussion about aromaticity. What does it mean to be aromatic? I did notice that I have a mistake on my worksheet. This fourth structure in is missing the rest of its other circle, its other cyclic structure. So right at the top where it just diverges into 2 lines, it's supposed to come back in and finish a 4th ring at the top. Okay, so the concept of being aromatic or having aromaticity is this electronic stabilizing force. When early chemists were doing the calculations, making predictions about how certain hydrocarbons should burn, what kind of energy they should produce, aromatic compounds that had aromatic rings in them, consistently defied their computations. So they realized that something special was going on with these aromatics. One thing that helped them kind of understand this better too was the resonance that happens inside of an aromatic ring. If we named this compound using the same rules that we do for alkenes, say that we need to count through an alkene in order to give it its positions, then these 2 structures would be different structural isomers. For instance, on the left, I can start numbering my ring where one of the methyl groups is right on a carbon-carbon double bond, and I can go through it to name the other methyl group right away. So this gives me 1,2-dimethylbenzene. This resonance form has a completely different name. This gets 1,6-dimethyl, which suggests that they would be structural isomers of each other, but they're not. And so in combination with stability and this lack of structural isomerism, people started representing these aromatic rings with a circle in the middle. I'm okay with you using that circle every now and then. I'm going to use that circle now and then because it just is so much easier than drawing all the lines. But there will be certain reactions where we need to show the pi electrons doing something, and representing them as a circle doesn't help. For instance, how many electrons do we represent every time we draw a line? How many electrons are we representing? 2 electrons. How many electrons are represented by a circle? Says who? So you guys are all just agreeing that a circle represents 6 electrons now? It didn't take you, it didn't take a lot to convince you to accept that. That's where the assumption is a bit dangerous, is that you forget what's actually being represented. And we'll talk more on Thursday too about how we can actually represent more numbers than just 6 electrons with the circle. Okay, so across the top there, you've got some other aromatic compounds. You're given a bicyclic structure that kind of looks like 2 benzenes fused together. In the arene family, this is called naphthalene. When you add a third ring, we make anthracene. And then my favorite, and you'll notice that this specific arene is actually on our Canvas homepage. This tricyclic structure that's kind of offset is called phenanthrene. And then the last one I wanted you guys to see is this tetracyclic structure that's called triphenylene. Triphenylene is used by my research advisor trying to work with highly conjugated pi electron systems. And you can see that it's essentially 3 aromatic rings fused to each other. Triphenylene. Tetracyclic, yeah. You see 3 aromatic rings on the outside, and they are all fused together, making a 4th ring. And depending on how you show the electrons, you could have also drawn a circle in that middle ring. But since we can't agree on how many electrons should be in a circle, since we're just kind of assuming it, if we drew an extra circle here, then we would start counting too many electrons. So I would show a circle to show that it has that aromatic character, but I won't because I think it'll throw off our electron count. It is an aromatic ring on the inside. Actually, the whole thing, the whole tetracyclic structure is an aromatic ring. All right, so if you look down on the left, I know there's a few more ring structures up there. If you look down on the left, you'll notice a molecular orbital diagram that explains some of this energetic stabilization. And I'm going to show you a method that we can use for predicting the energy levels of these MO diagrams. This is called a Frost circle. It is one of the learning objectives that I have for you to be able to represent molecular orbital energy using a Frost circle. A Frost circle tells you how many orbitals how many molecular orbitals an aromatic system will have and what energies they will be at. To draw it, you take the shape of your ring and you put it vertex down. So let's work with benzene. So I have my 6-membered ring, and I put one of its 6 vertexes straight down. The second step is to put a molecular orbital at each vertex. So for benzene, for my 6-membered ring, I create this hexagonal shape with 6 molecular orbitals. And for you guys, I've given you what the phases of those orbitals actually look like. You'll notice that we have these 2 sets of 2 orbitals, 2 equivalent sets. We call these degenerate. They're of equal energy, but they're distinct from each other. So you'll notice that they both have 1 node. But the way that node cuts through the ring is oriented different, creating unique molecular orbitals that both solve for that energy. Then you'll notice at the second level, there are 2 nodes, 2 different ways that you can cut through those orbitals, and the highest energy level had 3 nodes. So energy trends with the number of nodes in the molecular orbital. So let's fill in the electrons, because the molecular orbital is useful for telling us how electrons will behave. Well, electrons fill from lowest energy to highest energy. How many electrons should I start filling in? Since I'm looking at p orbitals creating pi molecular orbitals, I'll only consider electrons that are in pi bonds or electrons that are in p orbitals. Benzene has those 3 pi bonds, the 6 electrons, so I'll fill in 6 electrons into my MO diagram. The first 2 go into the lowest energy orbital, the next 2 separate themselves, and then the last 2 act as the pair. There's a little bit more math and a lot more drawing that we could do that helps you compare certain aspects about this MO to the MO of non-cyclic structures. But this actually provides a lot of stabilization for the compound. I'm not going to have you prove that that's how it does, so I won't give you too much more than that. But that's what I'll stake it on. The way that those orbitals are aligned up is what gives stability to the aromatic system. Oh, shoot. Okay. There are 3 rules called Huckel's rules, and we'll talk about them when we come in on Thursday. We'll use these 3 rules to look at a compound and say whether it's aromatic or not. And then we'll also look at how aromatic compounds and anti-aromatic compounds rely on hybridization. So we'll have some new rules for determining hybridization. Okay. Have a good night. See you guys on Thursday.